I'm going to get us started here because, again, as you know, we are on a little tight schedule. I want to show you as much as I can. I know it's impossible to show you everything, and so we'll see how much we have. As I think I mentioned to you, but it's probably worth repeating, there's one more major step in physics. This chapter, as well as the last chapter, were the applied physics. They were doing our circuitry, and I'll begin kind of reviewing what we've done so far in this chapter. But before I even get that far, I just wanted to lay out the rest of the semester. I think you know the plan, because I know it gets real busy and gets to be a challenging time, but there's I think 3 weeks left counting this week. So this week, as you know, we were working with AC circuits. We just got started on that. I'll review that in just a second, but that's chapter 33. And so my goal here today is to talk about the rest of 33, finish up 33, and with a little bit of luck, maybe get that last piece of physics out there in chapter 34. I'd like to do that so that it's out there now, and then I can say, okay, no new pieces of physics, although we got some things to put together for the next lecture on Tuesday, but that's, I think, better than giving you the last piece of physics on Tuesday. So that's kind of my hope. But in either case, we've got today's lecture and then next Tuesday's lecture. That's it. Obviously, Thursday is Thanksgiving, so there's no lecture. After Thanksgiving, a week after Thanksgiving, so 9 days from today is your last in-class exam. So that's it. Today's lecture, next Tuesday's lecture, and then the in-class exam on that Thursday. Following the next week, which is then finals week. So I grabbed the schedule here just to double check, and I'm going to ask you, what day is your final? Tuesday. All right. What classroom is it in? This one. Oh, this one. What time is it? 8 a.m. All right, so I want to keep emphasizing that. 8 o'clock, okay? So that's only 2 weeks from today. So 2 weeks from today, you'll be halfway through a final exam at this time, right? And so it's going to come quickly. Got another test in 9 days. Then 5 days after that, you have the final exam. Yeah.
Do we have any classes like for review and questions?
Oh, yeah, and I did want to point that out. I'm glad you asked. I started to pull down the screen. I put it up here so I could remember. But right here is the review. And so next Tuesday will be the review. And Don was...
That's with Don, though.
Yeah, that's with Don.
Yeah, no, I'm talking about our own classes for like the final.
Oh, no, we don't have a full classroom time. But no, this is the review, if you will. And then, yeah, and you know where to find me. And then Don, he probably hasn't said anything about the final yet. This was about the test, but he likes to invite you guys on Monday of finals week to come by and ask questions. And he doesn't put together a one-time review thing because of the different times you guys have finals, but encourages you to come with common questions if there's a group of you, and start to ask them. And so for you guys, you probably have a final on Monday, and then after their final, you will probably start coming around in the afternoon thinking about your Tuesday final, which I would assume would be this one. Although you could have two finals on one day, depending on how things pan out in the schedule. Anyways, that's the goal here. So I will pull this down and say, all right, let's begin where we left off. And to give you that big picture then, you might recall then that we were working with, eventually anyways, RLC circuits. Let me put it on the board here. We worked with inductors for the first time last chapter. And then if you recall the last chapter, I'll call it chapter 32, but we started that chapter looking at what is an inductor, and then we had LR circuits. From there, we put a capacitor in there, and we had LC circuits, and we learned that they oscillate. Finally, what we said is, what if you put all three of them together, and then you hook it to a power supply? And we even started off saying, well, it would be kind of boring if we just hooked it to a DC power supply. So let's hook it to an AC power supply. And that then was the start of chapter 33 here. And so that's where I want to go back to. And I said, let's take a look at this. This is the goal of this chapter, all three of them in series in an AC circuit. And we only have time to talk about the series. That's all that's covered in this book. I know you guys in circuits have probably done a lot more sophisticated circuits than this. But let's take a look at this. And so we started off with this idea of what is an alternating current. But what we had left off with then is let's look at these individually, one element at a time. And so we said let's take an alternating voltage and hook it just to a resistor. And so that's the circuit I brought up here and said this. What if you then say the voltage, which is a function of time, minus IR equals 0? And maybe I should pause. Where did that come from? Well, this is our voltage. And so we're going to write our voltage as some maximum voltage and changing with time. So it's a sinusoidal pattern that changes with time. And if we run that signal through just a resistor, it's going to get a little more interesting when we have the inductors and the capacitor. But if we run it just through the resistor and we go to solve this, we get a pattern that I don't think is too surprising. It simply says that the current would then alternate. The current would alternate with the same frequency. It would be what I would call in phase. That is, the voltage is a sine function. The current is a sine function. Now, the maximum right here, current, is of course related to the maximum voltage, but it has been reduced by this factor R, which again, I'm thinking none of this, and I'm hoping none of this is a real surprise. The only thing that we've really done here is we've gone from our Ohm's law way back in chapter 27 and 28, and all we've really done is said, take this and apply it to a voltage that changes with time. And so we get voltage and we divide it by the resistance. I would call this then just Ohm's law. But it would be an Ohm's law for an AC circuit. And so what happens is the maximum current is, of course, the maximum voltage divided by the resistance. And then, of course, it has a sinusoidal pattern. Let's hook it up here. And so we left off last time with this. We said, okay, here is a sinusoidal pattern. I'm going to feed it into my resistor. And then feed that back. And there is that circuit. Now, so we can see it a little bit better on the scope, let's make a couple of changes here. Let's start with looking at the voltage itself. And so if I look at the voltage, there it is. Maybe I'll even put a measurement on here or two. What is the frequency here? And so I'm putting in a sinusoidal source. Here it is. You can see it here go up and down. It is about 180 kilohertz. 178.776 kilohertz there. Okay, well, there it is. But let's also look at the current. And this is the part that, if you recall, I had to play a little bit of a game here because I had to put just a small resistor right here because, again, oscilloscopes don't measure current, they measure voltage. And so the little game we played, the same one you guys did with the oscilloscope last week and you will next week, which, by the way, there's no lab this week, I think you know, because of the Thursday. It's obviously Thanksgiving, but that also then affects you guys on Monday. So there's no lab tomorrow. So don't show up at 8 o'clock with a big surprise and go, oh, wow, I didn't have to get here this early.
We don't come to class, right? Do we come to class Thursday?
On Thursday? No class on Thursday either. No. Yeah, like I said. And there's no lab tomorrow, right. So no lab tomorrow, no lab on Thursday, no class on Thursday. eat lots of turkey, take a 15-minute break, and get right on your homework. All right. Okay. Yeah.
So over here, a little earlier, you were saying that the current is actually a sine function also.
Right.
If you multiply both sides, like if you divide both sides by I and multiply both sides by R,
Yeah.
you end up with the resistor being a sine function also, but how's that possible?
No, you don't. If I were to
Solve for R.
if I were to solve this equation for R, I guess it would look like this. R equals, and I would have the voltage, a maximum, sine omega t, right? Divided by the current.
And that's the sine function.
This one is?
Yeah, the right side.
Well, the top is a sine, but so is the bottom.
But doesn't that make R a sine function?
No. All right, so if I keep going, I would have sine omega t divided by the current. The current would be I maximum divided by sine omega t.
Oh, okay. That makes sense.
Yeah. All right.
Because it just didn't make
Yeah.
sense because the resistance doesn't change.
Yeah, you're right. It does not change. Exactly. Okay, so now taking a look then at the current also at the same time, and this is where we left off, we said this would be what the current looks like. In fact, let me just kind of change the scale a little bit here. And so, hopefully, again, not much of a surprise here that what I have is I have a sinusoidal function for the voltage and a sinusoidal function for the current. And that the current has that same sinusoidal pattern, except that the maximum current does have a little bit numerical value that is different based upon what the resistance is. And so sure enough, we have that pattern right here. Okay. Now, what if we change this? What if instead of feeding it into a resistor, we feed it into an inductor? All right, so I'm going to make some changes here. I'll change this to an inductor. What happens over here? Ah, good. And this is where it's going to get, as I said, much more interesting in terms of practical and useful applications here. If I write out Ohm's law, I have voltage as a function of time minus L di dt equals 0. Could you solve that for I? Yeah, so this is V maximum sine omega t equals L di dt. Maybe I'll go ahead and put the L over to the other side of the equation. And now how do I get I? Yeah, and so I integrate both sides with respect to time. What do I get over here? Well, there's the I. That's the whole reason of doing the integral. And the interesting part of this is what happens over here. What do I get here? Ah, good. So I'm going to put maximum over L. I'll leave that alone. When you integrate sine, what do you get? Isn't it a negative cosine? All right. And so negative cosine, let me just double check. Negative cosine, if I take the derivative, I get 0, 1. Yeah, I get a sign here. If I rewrite this by putting maybe the constants first, like this, and then putting a, well, let me put negative cosine for one more step here, and we can talk about that in just a second. All right, so I'll pause right there. But I want you to see something here. And the two big things to notice here is look at the equation for the current. Is the current in phase with the voltage? No. What you see here is a negative cosine function instead of a sine function. Notice what else do you see? What's the maximum current here? What does it equal? Yeah, it is Vmax, and again, divided by a number, kind of like we did for the resistor. I mean, isn't that what we did for the resistor? Except, notice what you're dividing it by. Notice the part you're dividing it by has the frequency in it. And so this kind of looks like Ohm's law again, where you're dividing it by some quantity, but this quantity is frequency dependent. We are going to refer to this as the inductive reactance. In other words, let's study this for just a minute. I really want to make sure this sinks in. The same thing's going to happen for a capacitor. And once you understand those two, then the rest of the chapter kind of falls into place. But this one here is really saying the current you get really can be opposed by this. And it's frequency dependent. I mean, let me show you all these. I think at this point maybe the best thing to do is to come over here and actually hook it up. So here, same circuit, except now I'm going to replace the resistor with an inductor. All right, so I will disconnect the resistor and move it out of the way. And in its place, I will put my inductor. What do you see? And maybe it would be helpful to even turn off channel 2, which is the current. All right? So there is the voltage. It's a sinusoidal pattern, right? It starts here at the origin. Let me turn on the current, channel 2. What do you see there? A negative cosine function. You see that it starts down here and goes up and down and up and down. And so again, notice a couple of interesting things here. And that first one being the current is not in phase with the voltage. There is a slight variation of 90, I shouldn't even say slight, it's a huge variation of 90 degrees. And so what ends up happening here, if you look closely at this, you're saying you first get voltage, a voltage peaks, then the current follows later. Yeah. Yes, so hopefully you're seeing Faraday's law in here, and so don't forget this. I mean, the circuit part of it is, and the math part of it is hopefully straightforward here, but never forget it comes from an important lesson in physics here, and remember inductance is just Faraday's law. And so remember that you get a voltage when there is a change in the current. And so hopefully when you remember that, it doesn't surprise you that the voltage comes first. In other words, here's what ends up happening. As this thing is changing its voltage, you try to first shove some current in there. And when you try to shove current in there, you get a back EMF. And so there is an EMF that way. And the whole reason you don't get any current at that point is because you've got a voltage from your source pushing this way, and then you have a back EMF pushing the other way. So in other words, you have a voltage in your inductor, but you don't have any current yet. And that's what I'm trying to get you to see here. The voltage and the current do not occur at the same time. The voltage occurs first. Then, of course, the current builds up, and then you get current. But the voltage is related to the change in current. And so you're going to get voltage first, later on, followed by current. If it helps, remember the name Eli. L is right in the center, stands for inductor. What's before the L? EMF. What's after the inductor? I for current. And so we often like to say, hey, let's remember this as Eli. So here is good old Eli. And in the case of an inductor, L for inductor, the EMF comes before we get current. And I don't know if that helps. To be quite honest, it doesn't help me. I like just to go back to Faraday's law and say, of course, I'm going to get voltage first. The voltage is created from the change in the current. I've got to get a changing of the current before I can get any current. And it's that changing of the current that first leads to voltage. So I get voltage first, then I get current. And again, that's hopefully what you will see here. And that's very different than the resistor. The resistor, we got the maximum voltage and the maximum current at the same time. They were in phase. But here, they're out of phase. And that has some very interesting and challenging consequences mathematically. Yeah.
It would be opposite for the capacitor.
Oh, well, we'll do the capacitor next, and yes, it will be opposite. Yeah. Okay. Now, notice a couple other things up here, or at least one other thing here, is that not only would we say here that the voltage leads the current, but we would also say, right in here, the maximum current you get depends on the frequency. What if the frequency is really, really high? What does that say about the current? Yeah, if the frequency is really, really high, then the current is going to be really small. Now again, maybe that goes back to Faraday's law here. I mean, let's ask this question. How come the current doesn't just go to infinite anyways? I mean, what is opposing the current from just getting bigger and bigger? I don't see a resistor in here. Is there a resistor? No. But we do have a back EMF. Exactly. And so just like in the one before this, where we had the alternating voltage and we had the resistor, you did not expect the current to go to infinity because there was something opposing the current. We called that its resistance. And we talked a lot about that back in chapter 28 and why there is some resistance. Now we have, for a slightly different reason, something opposing the current. What's opposing the current is the EMF that is produced because of Faraday's law. And Faraday's law says that the EMF produced is proportional to the rate of change. So if you turned up the frequency really, really high, what would that say? The back EMF is even stronger, and therefore the current should get less and less and less. So again, hopefully by thinking about Faraday's law, you see both effects. You see the effect that you got to have voltage before you get current, and you see the other effect that the amount of current you get is frequency dependent. High frequencies should give you very little current, and low frequencies should give you a lot of current. And in fact, you might even imagine before we started this chapter, if I put a DC power supply here and no resistor, what would you expect from the current? Yeah, go to infinity, right? Get bigger and bigger and bigger and bigger. And so sure enough, we would not have any changing field, so we would have no opposition, if you will, to the current. And notice I keep using the word oppose or opposition because we want to make sure that we keep this concept straight in our minds that what is stopping or opposing the current is not resistance. It is something else, and hence the name reactance. Inductive reactance. Doesn't it kind of look like Ohm's law? Isn't it voltage divided by some number? And there's that some number. And this is the new part. Like I said, when we just had a resistor, that I don't think surprised anybody. It said, oh yeah, well, the maximum current is just V divided by R. Exactly, because it was the resistance that was opposing the current. But what's new here is it's the induced EMF of Faraday's law that is opposing the current. And hence, we don't use the word resistance here. We use the word reactance, inductive reactance. Let's see if I can show it to you. According to this, I claim that if I were to change the frequency, what should happen to the current? Should change. Let me turn the frequency up. And so remember, this one here is the current, the one that is behind the voltage. And so if I take my little dial, oh, I can't go much higher, but maybe I'll go a little bit higher. Higher and higher and higher and higher frequency. And that's as far as that dial goes. But did you see it go down? In fact, maybe I'll switch scales and so we can see it. Let's see, we were about there, weren't we? And so I'll go higher, 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 higher. And you get the idea. The higher and higher the frequency, the stronger this reactance is. The stronger the back EMF is. And as a consequence of that, the less current I get. And so, again, the inductor can be quite interesting here for those two reasons. One, I'll say it again, the current and the voltage are not in phase. Two, the amount of current you get, or what we're going to call now the reactance, the stuff that is opposing the current from flowing, is frequency dependent. Depends on what frequency. I'll turn it down and you'll see, of course, just the opposite. But lower frequencies, 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 and I'm off the scale there. I think that's about where we started, right? And so the inductor, like I said, has a very interesting effect. I'll keep going, because you asked about the capacitor. Exactly, and you're going to see the same kind of game here. Yeah?
Can the EMF ultimately go to zero if you have like a DC?
Yeah. Yeah. Yeah.
Even though a magnetic field will still be in the inductor?
Yeah, well, the magnetic field will be there, but there would not be a change in the magnetic field, so there wouldn't be a back EMF. There would be nothing opposing the current. And so the only thing opposing the current would be what other things are left here, which would probably be the resistance in the wires in this one. Okay. All right, well, maybe it's worth at least writing it this way. Another way of writing a negative cosine function is to write it as a sine function that has been phase shifted backwards by 90 degrees, or pi over 2 radians, since we're in radians here. But the negative helps me to remember which way it is shifted, and so does the Eli, and more importantly to me, so does just the Faraday's law here, that I'm going to get voltage first, then I'm going to get my current. Okay. Well, let's go to our third element here. As many of you already mentioned here, what if this was a capacitor? All right, so let's give it a try. Let's take that same circuit and hook up a capacitor. And we can go through the same logic, different math, but same logic to find out what happens when a capacitor is hooked in an AC circuit here. All right, well, let's do the loop rule again here. All right, so voltage here. I'll put a current going this direction as a reference. So when the current goes this way, that plate becomes positive, that plate becomes negative. The voltage on a capacitor is Q over C, we learned, and it would be a negative number since I was going from the positive plate to the negative plate, just trying to keep track of my signs here. This then would be V maximum sine omega t equals QC, or Q would be V maximum times C times sine omega t. And so that would be the charge on the capacitor. Okay, fine. But what I'd really like to know is the current. So how am I going to get current from all this? Yeah, I'm going to take the derivative. So take the derivative, that should give me the current. And it's, again, watch the math here. When I take the derivative, what do I get when I take the derivative? Yeah, I got a little piece of the chain rule here. Sine becomes a, is it just a plus cosine? Okay. With an omega. And so the current is equal to this crazy number, and then it's a cosine function instead of a minus cosine function. Okay? Let's look at it here a little carefully here and begin to say, does this make physical sense? And let's hook it up and see if that's true. But here's what you hopefully notice. Is the current occurring at the same moment in time as the voltage? No, not at all. Yeah, question.
Quick question. What's the value of omega?
Well, omega is related to the frequency. It's 2 pi times the frequency. Yeah. And so in my case, it would be 2 pi times 180,000. Okay, now, again, pause and look here at the physics, and I think this will help you remember that no, they're not in phase. The cosine function looks a little bit different than the sine function. In fact, which one comes first here then? Yeah, if you look at a cosine function, and maybe I'll just hook it up here. And so you can see it a little bit better. I will take this capacitor and hook it up. I'm going to change the frequency dramatically though. Okay. In fact, I'll turn off channel 2 just to kind of show you. So again, there is the voltage. And so there's the voltage, there's a sinusoidal. If I turn on channel 2, there's the current, right? And it's a cosine function. And so in this case, like the inductor, they're not in phase, but unlike the inductor, which one came first? Current. Why? And I don't mean why from a mathematical point of view. Cosine function is different than a sine function. I realize that.
Another way is that it's like an open circuit.
Okay, so to get voltage,
Closed circuit.
to get voltage on my capacitor, what do I need? I need charges there. In order to get charges there, don't I have to have current first? So the charges build up because of the current. So again, looking at the physical picture, hopefully it'll keep you straight. Which one comes first is, in order to get voltage, you first have to have current. So current would come first, then you would get voltage. That's exactly the opposite of the inductor. The inductor, how did we get voltage on the inductor? It was related to the change in the current. So we first tried to put the current in, and that's when we got the voltage. And it wasn't until later the current built up. So on the inductor, we got voltage first, then we get current. But on the capacitor doesn't have any voltage until after charge has built up. So you got to have current going in first, then you will get your, then you will get your voltage. And so sure enough, it peaks, and we get the current first, followed later by the voltage. If it helps, I like the word ice here. Because again, the C for the capacitor. What happens before the capacitor? I, current. And then after? The EMF. And so here the EMF follows behind the current, or the current leads the EMF. And so if you've got extra time to kill, do yourself a Google search for Eli the Iceman. There's a lot of little comic pictures, but they're all related to electronics. They're a nice phrase. And Eli the Iceman, it looks like this frozen tundra guy who has all these pics, and he's an expert in electrical engineering here, okay? But it's, like I said, kind of a creative phrase of remembering it or trying to remember it. And I know it's worked well for my students in the past, so I keep repeating it. But for me, the physics is a little more my liking. Makes sense? Hey, if I'm going to get voltage on a capacitor, I first got to charge it up. I first got to get current. The inductor? Well, I'm going to get voltage first because I'm trying to shove current in there first, and that's what gives me the voltage. And so it's Faraday's law. So Faraday's law for the inductor, or Coulomb's law for the capacitor, hopefully we'll keep these together in your mind.
So combine the capacitor and the inductor, you have a very hard time pushing it at all.
And we're going to do just that in just a second here, but there is our basic physics here. Now let's keep talking about this, okay? Notice something else here. Kind of like the inductor, but opposite. Isn't this the maximum current right there? Isn't the maximum current related to the maximum voltage, but other factors like frequency? And this, I got to admit, looks a little funny, but it is very useful to write it as 1 over omega c. Isn't that the same thing? But if I come back over here to what we did with your resistor and what we did with the inductor, both of them had the nice little option of writing it kind of as the maximum voltage divided by something. And that something was the opposition. And here we called it the resistance. And here we called it the inductor's reactance. So guess what we will call this? This too is a reactance. It is a capacitive reactance. Now again, let's see if we got a good understanding of this. Let's start with the frequency. If you wanted to get a lot of current, would you have a high or a low frequency? High, right? And maybe mathematically it's easier to see here. But if for this current to get really big, then you want the frequency really big. But when the frequency is really low, the current is really low. So again, the amount of current is frequency dependent. It's exactly opposite to the inductor. You saw me turn up the frequency and the current went down. Now I will turn up the frequency and watch the current go up. And so I'm going to come over here and change the dial and turn it up. And so we'll go up, 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 up. And as I go to higher frequencies, what do you notice about that one that's leading? Doesn't it get bigger and bigger and bigger and bigger and bigger? Exactly. And so again, interesting, like the inductor, but the opposite. The inductor and capacitor both have what we call a reactance. They oppose the current. Now, again, both of these are a little bit different, and different than the resistor. The resistor opposes the current because of its resistance, hence we call it a resistor. But the inductor opposes the current because of Faraday's law. I would say the capacitor opposes it because it builds up charge, and that's an electric field created by Coulomb's law. Maybe it's worth repeating. There are two ways to create an electric field. What are they? charges and changing magnetic fields. And so this guy here, the inductor, was opposing the current because it was creating an electric field by this second way we learned, a changing magnetic field. But now this capacitor brings us all the way back to the beginning of this semester, where this guy opposes the current because of just the charges that are there, just the Coulomb's law. And so we like to write this then as the maximum current in your capacitor is the maximum voltage divided by the reactance of the capacitor. And so each of these elements oppose the current. A little different reasons and a little different behavior, but they all have some kind of opposition for making the current be very high or going up too high. Yeah?
Does the capacitor ever get charged fully?
I mean, just that phrase, does it ever get charged fully?
Like fully charged in a DC circuit, we have to find like the full charge of the capacitor.
Yeah, but it's that phrase, fully charged. Remember, a capacitor, when we say capacitor is 10 microfarads, it doesn't mean it's fully charged when it's at 10 coulombs or 10 microcoulombs. What we mean is it gets 10 microcoulombs of charge for every volt. So if you have a capacitor that is only hooked to, say, a 6-volt DC battery and it's 10 microfarads, you say it's fully charged when it gets to 60, right? Because you get 10 microcoulombs for every volt. We have 6 volts. And then, but with an AC circuit, the voltage keeps changing. So I guess what I'm saying here is we don't really have what we would call a full capacitor. A capacitor doesn't get full. It's not like a 5-gallon bucket where when the bucket is full, it overflows and we say it is full. Here, the voltage always changes, hence the charge on the capacitor always changes. So it never reaches like a maximum and stays there. So if that's what you are after. Okay.
So it never really charges at all.
And so the capacitor charges up. Now, how much does it charge up? Well, that all depends on time and depends on this frequency. And again, that's why at the high frequencies, how much current do you expect to get at high frequencies? A lot. And the reason for that is because the capacitor never really gets a chance to build up much charge. Because you start to put charge in there only to switch and discharge it right away. And because you never put much charge in there, I would say in that sense, and I think that's what you were after, I would say the capacitor never really gets charged up during the high frequencies. And if it doesn't get charged up, that's why the reactance is small at the high frequencies.
So does it depend on where you disconnect it throughout the wave? That will tell you what kind of charge you have on the capacitor?
Oh, right. So if I, let's see, I guess I'll turn the frequency down a little bit. So maybe we can kind of see it spread out there. But in this case, the capacitor, well, this is the current. The charge, coming back to, say, this step here, the charge on the capacitor is sinusoidal also. And it is in phase with the voltage. It makes sense. These two have the same voltage on them. So I don't really have the plot of charge of the capacitor up here, but you could say it's this one here. And this one here is saying that the capacitor builds up a charge and then it loses its charge, and then it gets charged up the other direction, and then it loses that charge, then it gets charged back up the other direction. So there is a charge that changes with time on the capacitor, yes. Yeah. And so, again, let me just emphasize, hopefully you see Ohm's law here in all three cases. And in fact, that's worth putting over here on the sideboard so we can put everything together. Yeah.
The rate of charge is controlled by the voltage rather?
So the frequency is controlled by this guy?
No. Right. The frequency is that will control the charge and discharge.
Yeah. 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 So again, high frequencies are. So why did we do all this? Well, again, the point in all this was to get to this. What if I have all three of these? Let's take a look at this. I'll kind of clear this off here for just a moment and say, what would happen if I had all three of them? And so I will start over here on the side with this case, which says that you could have the effect of just the resistor. You could have the effect of just the inductor and the effect of just the capacitor. Again, let's talk about each of those. For the resistor, you get some opposition to current flowing, called its resistance, okay? For the inductor, you get some opposition that we call the reactance, inductive reactance. That is the one, if you recall, that depends on the frequencies. And so high frequencies give us very little current. The third one, the last one we did here, same idea, that the current is again controlled by the reactance. This reactance is coming from the charge building up on the capacitor. It is equal to AV over 1 over omega C, which I like to write as a V omega C. But again, you can see with the omega in the numerator instead of the denominator, you can see that high frequencies, this one wants to go through. So what do you think you would happen if you had all of them hooked up?
Very hard to push.
And so as you try to push this way, if you were, say, at a high frequency, do you think you'd get much current through here? No, why not?
Because the capacitor will push, the inductor will push back.
Yeah, the one that doesn't like the high frequencies is this guy. This is the Faraday's law. You're going to get a back EMF that's going to be pretty strong. So are you going to get much current here? No. Oh, what about low frequencies? How much current do you think will go through here at low frequencies?
That doesn't like it, so.
Yeah, and so you get a back EMF from the capacitor. Maybe back EMF is a terrible word to use because we usually save that for Faraday's law. But here you get some opposition due to Coulomb's law, building up of charge, because of the low frequency gives a chance for the capacitor to build up. But the point is, you would not get much current either at high or low.
So is this like a frequency sorter?
Yeah, and so this is what we're going to call a frequency selector. What about that mid-range? Yeah, and there's a middle range in here where these two guys, and here's where we have to look carefully, these two guys are actually adding together, or helping each other, I should say. Now remember, that might be a little bit tough to digest here at first, but remember that these two are changing their voltage. This does not like high frequencies. This does not like low frequencies. But aren't they also opposite of each other in terms of their current? Here's what I'm trying to say. If I put all three of these together, I would have I better give myself some room, the voltage from my AC source. I would then have minus IR. I would have minus L di dt. And then I would have the minus Q over C equals 0. And what's interesting here is this is not just a simple arithmetic. This is a trigonometric arithmetic. These things are out of phase with each other, right? I mean, maybe a picture over here would be quite helpful. And in fact, your author does do a good job with a picture. Let me switch it back over here for just a second. He says if you were to hook all three of these together.
And could you like just replace those with I times inductive reactance and I times inductive?
Well, I'm glad you asked, because this is the challenging part here. Maybe I'll call this picture up first. But this is what I'm talking about here. I've got the voltage from the resistor, the inductor, and the capacitor. And when you add them together, you must remember that you are adding trig functions that are not in phase here. So again, let's take a close look at this. The reason your author does the series one first is let's look at that top picture. That top picture is saying, all right, whatever happens, whether it be a lot of current or a little bit of a current, and you already told me it would be very little current if we were at high frequencies because the inductor would stop it. And it would be very little current if we're at low frequencies because the capacitor would stop it. Fair enough. And I'm trying to convince you it's even more interesting in the mid-range because you will get some current through there because these inductor and capacitors, although they are blocking, they are out of phase. Watch. And here's your author's point here. He says, let's let the current be a sinusoidal function. Now that's where I can lose you here, because I think up until this point I have always treated the voltage as the sinusoidal function. Fair enough? So we're going to make a switch here. Did you catch that? Okay, so the author's going to take a little bit of switch here, and instead of saying the voltage is always sine omega t, let's say the current is always sine omega t. Because why? What do you know about these three elements? They're in series, so don't they all have the same current in them? And so your author says, so let's treat the current that is going through here as some maximum current times sine omega t. Okay? So I want to say it again. That is not what we were just doing. We were doing the reverse. What we did is we started with a sinusoidal voltage, and from that showed how the current was related to it. So we're going to kind of work in back pair here. Because if we let the current equal that, look what we have here. We've got this term, which is V maximum sine omega t minus I maximum sine omega t times R. I'll put the R with there. Then we got minus L. Oh, what's the derivative then of the current? Yeah, I max omega. And when you take derivative of sine, you get cosine omega t minus, here's capacitance. How do I get charge? So I need to integrate this. So if the, see if I said this right, if the if the current is a sine function and I integrate it, what do I get? Yeah, can I put the negative out in front? Cosine omega t over omega. Right? And so this becomes, in place of q, I've got a negative, so there makes a positive there. I have, see if I've done this right here, I have an omega down here. I get an I maximum, and I get a cosine omega t. Now I think you're beginning to see the math here, that when I put all three of these together, you can begin to see, as we mentioned earlier, how come I would not expect a lot of current when we are at a high frequency? Because that number is so big, right? Why would I not expect a lot of current when I'm at a low frequency? Because that number is so big. But did you catch how these are opposite? And so if we look closely at them, when would you expect to get a lot of current? See how these can cancel each other off? I mean, I'll go through some more math because I want you to see it at any frequency, but at just what I would call the correct frequency. Maybe I should say best frequency. Kind of depends if you want current. If you want current, then there is a mid-range here where the Li maximum omega equals I maximum over omega c. At that particular point, omega squared equals 1 over LC, or omega equals 1 over the square root of LC. If you are at that frequency, what is really beginning to happen here is you are getting a voltage from this guy and a voltage from that guy that are equal in magnitude but opposite in direction. So the only thing that is equivalent to opposing it is the resistor. At any other frequencies, then one is bigger than the other, and you're going to get a opposition that is greater than just the resistor alone. But this is the point where it is essentially the same as if you never had an inductor or a capacitor hooked in the circuit, and the two balance. And that's this mid-range. Yeah.
That also says that when the inductive reactance and the capacitive reactance are the same, it's also the maximum.
Right. Now, if you wanted to kind of add some of the math we've already have, you can kind of see it here that this is the reactance of the inductor times the current in the inductor. And this is the reactance of the capacitor times the current in the capacitor. This is the voltage on the inductor, and this is the voltage on the capacitor. So, yes, I am saying that when the two reactants are the same, hence the voltages are the same. But don't miss the important. They're the same but opposite in direction. And I think when you just write it this way, you lose the fact that they are plus and minus. They are equal in magnitude. They are opposite in direction. And that's the key understanding to realize that they are essentially canceling each other off. And what you are left with is your voltage from your power supply being opposed by just the resistor, and it's as if those two don't exist. And that's why you get a lot of current. And how much current would you get in that case? Well, you get just that, right? You would get your voltage divided by the resistance. The inductor and the capacitor have buddied up, if you will. They have canceled the effect one from another. And what makes that interesting then, as you said, Danny, is this is now a frequency selecting device. It will not let high frequencies. It will not let low frequencies. It will only let that mid-range. Yeah, the right frequency. This one right here. And this is kind of fun to watch. So let's hook this one up so you can see the actual physics of it. Yeah.
Doesn't omega equal 2 pi f?
Yes.
Okay.
Yes. So this one, and I called it up and I didn't really use it, but I think now you can see that here's what the author is saying. He goes, in order for this to work out right, yes, there's no new physics here. Yes, it's just Kirchhoff's laws, but you have to add trig functions. And we are going to do a lot more on adding trig functions here in just a second. But I'm going to start with the easiest case. The easiest case is, could we add these three trig functions together? This one's a sine, this is a cosine, a negative cosine, and this is a sine. And that's what your author has here. He says, here's the voltage from the resistor, it's a sine function. Here is the voltage from the inductor, it is a cosine function. And here is the voltage from the capacitor. It is a negative one. Now maybe I should be a little more clever here, is he did change his equation. And so maybe I should make it look like his, because he moved this to the other side. And so he gets I maximum R sine omega t. You see, that's why he wrote it as a positive sine function. In my equation, I still had a negative in front of it. So I'm going to move it to the other side to match his. All right, so what he's saying is add the voltage from the resistor. So that's what happens when I move it to the other side. Add the voltage that you get from the inductor. And so notice when he moves it to the other side of the equation, the negative becomes a positive. So he says add the voltage from your inductor. It's a positive cosine function. Again, add a phase is both the interesting part of it in terms of applications, the hard part in terms of mathematics, because now you're asking me to add trig functions together. And don't you just love trig identities? Actually, we're going to avoid it, but nonetheless, that's what it's looking like at the moment anyways. Move this to the other side, and this would become a minus, and it would be xc maximum cosine t. Okay? And so that's what we're working on. We're working on trying to understand what is the maximum current. And what I said was, if this special case is met, if, so maybe I should put, if the frequency is 1 over the square root of LC, then these two numbers here, right, are equal. And if those two numbers are equal, then these cancel off. And then it is very easy to get the maximum. The maximum is just the Vmax divided by R. And so this is our special case. And it's really what I want to focus on, because that's what I was trying to say here, is there is a nice special case. There's a case where if the frequencies are too high, you don't get any current because the inductor stops it. And at low frequencies, the capacitor stops it. But in that mid-range, the two are about equal in strength but opposite in direction, and you end up getting a lot of current. And so let's take a close look at this. Yeah.
So is it just one frequency that we're going to get, or is it going to be a range of frequencies?
Well, it'll be a range. In fact, maybe I will show you the graph before we even get to the solution. But we're about to solve this equation, and we will see something like this. The oops, not that one. We will see something that looks like this. If I were to plot the current on the vertical axis versus frequency, then in this range over here, I would get very little current because of the inductor. In this range here, I will get very little current because of the capacitor. And as I get closer and closer, so it's not just one frequency, but as I get closer and closer, I will get more and more current. So that's kind of jumping ahead a little bit since you asked, but I do want you to see the concept first, and then we'll solve the math. But we can still solve this. We're not done. We're not even close to being done. We got a lot of work to do here. But we can find the solution for the current at any frequency, not just this mid-range. However, I do want you to see this mid-range to convince you it does work. Yeah.
According to that, apparently there's a small bit of tolerance.
Yeah.
Is it possible to widen or shorten that tolerance?
Oh, yes, absolutely. And how much it widens or shortens, I think you will see in just a second when we solve the whole equation. In fact, you guys have me tempted to solve the whole equation now because you keep asking some good questions. But I feel like I should show you this to you. So I'm going to switch back to the oscilloscope here and say, let's hook up all three of these. All right, so we left at a fairly low frequency with just a capacitor. Let me put the inductor in here also. So it looks like it came to the capacitor, and then I'll just leave it there, because from the capacitor, I will feed it to the inductor. And from the inductor, I will go back to the resistor, and I will have my L, or I guess in this order it's C, L, R. I think your author has it as R, L, C, but they're all in series, so it doesn't matter which order we put them in. But I have a capacitor, an inductor, and this is my resistor that is just looks like it's set at 30 ohms there, but I'll just leave it there. But it's a good way of measuring the current. The answer is the capacitor is 1 microfarad. Oh, the inductor we didn't measure today, but we did the other day. What was it? Was it 0.3 milli? 0.13. Yeah, that's right. Yeah, good. 0.13 millihenries was it? In fact, I wasn't going to do any math, but now that you brought it up, why don't we check out the math? What frequency would I expect to get for this to be what I'll call the magical frequency here? And so I should have 0.13 milli and 1 micro. That should give me, all right, well, let's see what I get. 0.13 milli times 1 micro, square root of that, and reciprocal. Then divide it by 2 and divide it by pi. We're looking at about 14 kilohertz. And so I would expect this thing to get a lot of current around 14. So let's take a look at what I have right now. What I have right now is far below 14, right? I have about a 300. What do you notice? Well, hopefully you notice doesn't the current come first and then the voltage? Doesn't this kind of look like we just got done with just a single capacitor? Exactly. Because what is really happening is we are at such a low frequency. What's doing most of the stoppage here? It's the capacitor. Doesn't surprise me that this looks more like a capacitor than anything else, because we are at such a low frequency and such a small then amount of current that the resistor really isn't doing much of anything. And the frequency is so low that because of Faraday's law, the inductor really isn't making any voltage stoppage. And so we know when we have a capacitor, what happens here is we get current first, then voltage, and we don't get much current. Okay, let me up the frequency, and not by a little. Let me change it by a lot. Let me just change a whole setting way over to 180,000. Maybe I need to spread out the time frame here so we can actually see it a little bit better. Okay. And so now I'm at a really high frequency. We're back to that 180,000. Now again, what does this look like? Now if it helps, maybe I should, well, I think you can see it. Here's the voltage again. When do we get the current? After the voltage. And when did that occur? For the inductor. Now again, maybe that's not a big surprise here, because again, I am at such a high frequency that essentially what is happening is the inductor is stopping it. The frequency is so high that this never gets a chance to fill up. In fact, the frequency is so high that the current is so low that really this would not even charge up if there was a long period of time, because the current is so low. And in fact, that's why the resistor is essentially not doing anything either, because the current is so low. And so it's essentially both of these aren't even there. We only have the inductor. And that's what we saw a half hour ago when we dealt with an inductor. And so there are the two extremes that hopefully aren't a surprise. So now I can maybe get to this middle ground that I'm trying to show you. What then happens near, is that what you got too, by the way, 14,000?
Yeah.
What happens near my 14,000? And so I will change the dial, 14,000. Maybe I'll leave it on that setting and go way down. Oops, I think I'm going the wrong way. Ah, there is about the 14,000. Looks like I'm going way off the screen. Let me turn off the current. I think that big one's the current. Yep. All right, so there's the voltage. Okay. Maybe I'll even make it a little taller if that helps. Okay. And actually, let me center it up so it looks like a sine wave there. Okay. So, but there's my sine wave at about 21 hertz. Let me turn on the current. And the current right now, in fact, it's off the scale, so let me kind of lower it down a little bit. Right there. If I then change, and it looks like there is probably the best effect where they cancel each other. Notice the peak of the voltage and the peak of the current are acting together. This isn't exactly the idea I was trying to say when I was said here that you will get this large amount of current. If I go to frequencies that are higher than this, which I guess I should put the frequency back on here. Is that around 14,000? Yeah, okay, so 13,000. If I turn up the dial a little bit, can you see the current coming down? And so the current comes down. And not only does the current come down, but the phase relationship begins to look more like an inductor. We have voltage first, then we have current. If I turn the frequency down and get back to that peak value, which we're going to now start calling its resonant value, right there, boom, right there. That is the maximum current. And by the way, it's probably more maximum than you might realize. I don't know if you noticed, but did you notice how much the voltage draw is dropping too? So unfortunately, the voltage dropped here. Watch, if I wanted to compare apples and oranges, or apples to apples instead of apples to oranges, if I put it right here, notice that the voltage is going up 2 divisions. Right? So if I were to change the frequency to right there, and then increase the voltage to 2 divisions again so I can compare, that's how high the current went. The current went way, way up there. If I go to lower frequencies than this, and I'll have to change scales here, but if I go to lower frequencies, see how the current comes way down, even as the voltage went way up. And so right there, if I kind of sweep through, it peaks up and comes down. Peaks up and comes down. And that's the physics I'm trying to show you. We still got a lot of math to show you, what if you're not right at that value, but I am trying to show you that there is that magical frequency. Yeah.
I was wondering, which one, at the perfect frequency, which one's the voltage across the voltage that's delivered by the power source?
Well, they'd be equal at that point.
No.
When they're at resonance, these two are canceling off.
Oh, they'll.
And so it's just back to the simplest case right here. I thought it would be fun to actually give this a try here. Let's do this for a moment. Let's disconnect this circuit and add to it a little bit here. All right? So, whoops, sorry. All right. So, let's add to this by taking this contraption, and I don't want to mess too much up here, but let me disconnect it just right here for a moment. Okay? And so I'm going to hang that one down here. So this LCR circuit is not hooked up. Fair enough? The only thing I'm looking at and maybe right there is the voltage coming from my power supply, which is about 16 kilohertz. Fair enough? Because I have another box right here. This one is set at a very low frequency. For those of you who are close enough can see, it's somewhere around 2 or 3 hertz. Okay? What if I were to hook the two together? What would I get? Well, I'd get 2 different frequencies, right? I would get this one frequency that is at 16 kilohertz and a second one that's at 3. Okay? And it looks like it gets deformed down at the bottom, so I'm going to make a little bit of an adjustment here. Okay. Okay. So, fair enough. Does that look like 2 different frequencies to you? A really high one at 16 kilohertz, or I'll call that mid-range, and then a really low one at 3. Let me keep going. Let me hook up a third one. Oh, I'm going to block your view. I'll leave it down here. I want you to be able to see the number, though. Can you see the number if I put it? Maybe I'll open the ears. Oh. All right, take that off. All right, but I want you to see this is another source that's set at a pretty high one. This is a 1.1 million. Let me hook it up. Now, just so that we don't have both at the same time and confuse you, I'm gonna disconnect this one, okay? So that one goes away, and they also interfere. I'm gonna put the high frequency on here. Okay? And that's gonna be kind of hard to see, so I'm gonna play a little trick game here. And forgive me for a second, I'm gonna make a quick change that I won't really explain, but at least we'll be able to kind of see what's going on. In fact, that frequency might be a little bit higher than I want it to, so I'm going to turn it down. So maybe you can kind of see.
Converts the sine function into a sine function.
Okay, so again, I am having this here, which is this main frequency, the mid-range, the 16 kilohertz, and I'm feeding on top of it about 1.8 million, okay? And so that's this crazy one. Fair enough? All right. Shall we put all three of them together? All right, so the point here, I have three frequencies, don't I? Right? The three frequencies are this main one, the mid-range, the 16, then a low one, and then a high one. I've got some dials here that I can turn off the amplitude of the low one and turn off, kind of off, the high one. Didn't completely go off, right? And so let's take a look then of when I have a little bit of high frequency, a little bit of low frequency. What do I get when I run all these through this LCR circuit? And I look at the current on channel 2. What do I get on channel 2? Shall I turn off channel 1 so you can see it better? Isn't channel 2, the current, really just the 16 kilohertz? I mean, it's not perfect, I agree. And you see a little bit of the bouncing and you see a little bit of the high frequency, but didn't it pretty much stop the low frequencies and the high ones? Watch, just to convince you, let me take yet another wire. Isn't it the capacitor that is blocking the low frequency? So if I were to bypass the capacitor, what do you see for the current? You see that low frequency. You see the 16 and you see the low, right? But when I put the capacitor into effect, what happens to that low frequency? Right. It is blocked. Maybe it would be more convincing to you if I did it this way. Without the capacitor, that's what I get. I get both the 16 and the low frequency. I do it this way. The capacitor is blocking the low frequency. What's the inductor doing? It's blocking the high frequency. So what if I were to do this? What kind of current do I have in my circuit? I get the 16 and this high frequency. And so as you pointed out here, Danny, this is a filter. It is a frequency selector. I'm actually feeding in something like this, something quite complicated. In this case, made out of 3 different frequencies. And the only thing that gets through is the magical one that I've tuned into. And this is really no different than you talking on your cell phone, than you listening to the radio, than you surfing the internet, than you hooking up the Wi-Fi. Because when you hook up to your cell phone, do you really want to hear the conversation of every frequency of every other cell phone that is going on out there? Some of you might say yes to that. You should, and maybe you should work for the NSA. But Most of us can care less about all the other. What do we want? Just our frequency. And when I get in my car and I tune that radio and it goes 99.9, that's the frequency I want. I want K-tide. That's it. I don't want any other frequency at that point. Then they'll go off at a commercial, so I switch it to another channel right away here. But whatever it is, I use the electronics in my radio to say, give me that frequency. Give me 95.9 till they go to commercial. Then I'll go to 99.9, and then I'll go, and then I'll go. And so I select, despite the fact that there's all those frequencies out there, we've got people on cell phones, we've got other radio stations, we got AM radio stations, we got communications between police, fire, and of course along the coast here, all the coastal navigational equipment. I don't want all those. I want just my one frequency. And this will do it. And that's the whole lesson here. Yeah.
Are those like how rectifiers and diodes make?
Yes, and you probably remember me passing around that FM trap, and you saw all those inductors hooked up there. That's what that was doing. It was trying to select the frequencies to let through some and to dump others. And so that's essentially of what we just have built. Of course, now we got a lot of math to do. Can we mathematically show that? Yeah.
Is that like a sudden range of frequency that can be used?
Yeah, so that graph, which I'm about to derive, that graph then really says there's a range of frequencies that can get through. Anything that's way lower or way higher won't get. So you'll notice I used way high and way low. You know, 16,000 is what I wanted. This guy's only at 3. So I got rid of them. And this one is at, 1.8 million. So they're far away from the 16.
With cell phones, are we ever going to run out different frequency in each cell phone?
Oh, cell phone's a little different. Maybe the cell phone was a bad example because the cell phone's digital. And so the better example is the radio station. And yes, there's only so many frequencies, and then we would run out. Now where we live, we're not even close to running out. If I go through the FM dial, you'll notice that there's a room for a new station every 0.2 megahertz. So, if I go to K-tide 99.9, the next possible one is at 100.1. I don't think there is a station there. When you drive down to LA, it seems like every time you move it, there's a new radio station. They're pretty full. It's like, okay, no more room for radio stations. Yeah.
How do cell phone towers control the frequency? Like let's say you haven't paid your bills on your cell phone and you can't use your phone. How do you control that?
Well, it's a software. It's more of a software. And so that's what's different. It's sending a digital signal and saying, hey, this is my phone, let the call go through. If you don't pay it, the software says.
You just tap the same frequency and still frequency?
No, because very different. It's not just the frequency. Then it's a digital code that is sent in. And so you're sending out a frequency, but it's not really, it's not different. Cell phones are in different frequencies. So that was probably a bad example. They're pulsating a code, and this one is pulsating a code. And there's a range of frequencies within that code. So I'll lay off that. But
all phones have their own identification number that the carrier knows, so that's how you know it's yourself.
And then it gives that code. So yeah. So that was bad example, I suppose. So it's not different frequencies. Well, it kind of is that too, but they're different ranges of frequency. I guess is what the
bands, they work on the 800 megahertz band. I think you can hear.
Right, and then you can code so many at that band, and then you can go to another band and code another so many. Yeah. Okay, well, before we run out of time, which we might anyways, is let's start adding these together here. And so now that you've actually seen it, let me switch back over to the computer here and go back to this picture here. Okay? This picture that I was starting to do and said, okay, let's add these together. Here is really the math. The math is saying, could you then solve this equation for the maximum current? And I claim you can. Like I said, so far, took the easy way out and I solved it at the special case. I solved it for the maximum and said, okay, at this frequency, you will get this much. And I tried to show you that. And I tried to show how then that when you were at higher or lower frequencies, those get blocked, but the mid-range got through. And I claim we can derive that. We've got a little bit of work to do, but see what we have to do is we have to then factor out I max. And when we do that, we will then have adding together our sine function added together XL cosine function minus XC cosine function. How do you add sines and cosine functions? Trig identity is one option. I'm going to elevate your education here a little bit and talk about phasors. Ooh. That, I suspect, is new for a number of you. What the heck is a phasor? See if this helps. I'm going to show you a little picture. Let's just look at a sine function. Let me leave this math alone right here. Let me clear off this part of the board and say, all right, I'm going to add a bunch of trig functions together. But let's just start with a visual picture. And when you see this, you'll see how easy it is to add trig functions together with phasors. But let me do a stop here for a moment. And let me put the phasor, if you will, right, oh, that's not what I wanted. Right there. Okay? Now, I think you'll recognize this as a trig function, right? You might call it a minus sine function instead of a sine function, but it is definitely a trig function. Okay? Now, here's what I want you to see. You can either look at a trig function like this, or where did this actually come from? This thing that is spinning is called a phasor. In other words, if I were to start the clock a little bit, and I take this, I'll call it a stick, and spin it, isn't the projection of the stick on the vertical axis that? And so if you have a stick and you spin it and you look at its shadow, the height of that shadow, this, doesn't it trace out a trig function based on this sign, right? So if I were to draw this stick pointing out there and call that the phase, then isn't the height of it sine of that angle? All right, and so I want to give you a new way of thinking of trig functions if you haven't seen this before. It's a visual effect. So instead of thinking of a trig function as a wavy looking graph, think of it as a spinning stick. Yeah.
So are you saying the cosine and sine are the same thing but off by 90 degrees?
Exactly. Yeah. All right. So if I were to go step by step by step, then that would be the maximum, right? And so in this case, my spinning stick is in this location. And so that is projected onto here. If time continues on, I would have that, right? So again, two ways of viewing a trig function. This one, which is mapping out a curly wave, and that's, I'm sure, how you were first introduced to trig functions. This second option is a spinning stick, which some of you have been, I can tell by the look, and others of you have not been introduced to phasors. And so again, the best thing I can say is imagine a stick and you spin it. And as it spins, the shadow created is plotted. And so our two options of looking at trig functions are a wavy pattern that is kind of stationary, or a spinning stick. And I really like this animation because your book tries to teach you phasors, but when it's on paper it's kind of hard to see a spinning stick. And so your author says, let's go back to the resistor for a moment. If you look at those trig functions and you go back to a resistor, this is what you might call the phasor diagram for a resistor. What did we say about the current and the voltage in the resistor? They are in phase. So what your author is trying to say here is if you were to look at a spinning stick that is representing this trig function, it would be sticking out a length of r. He calls it I times r for the voltage, but let me just call it r in mind since I already factored out the I. Okay, but if I have that trig function, that's how I would represent it. R, and the sine function would start at 0 and get bigger, 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 maximum. Smaller, 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 0. Negative, negative, negative to a negative maximum back to 0, right? And so I'm hoping that in your mind you don't see a static picture in here, but you see this brown stick spinning. And so that is my first trig function. So, again, you can think of this as something like that, or something like that. Let's do this. You'll see how much better it is in just a second. All right? And so that's the idea of a phasor. Now, just to make as a reference, your author puts the current in there too. Because didn't we start the beginning part of this and say the current is in a sinusoidal pattern and it's a sine function? And so the current in the resistor and the voltage on the resistor are in phase. Isn't that what we learned about resistors? So that's why your author has two sticks. That's why I grabbed these two so you can kind of see. Your author is trying to say one stick is representing the sinusoidal pattern for the current. The other stick is representing the sinusoidal pattern for the voltage. And so you have something that is spinning like that. And that is mathematically how I would represent that function. Let's go to this one. Let's go to the inductor. What would the inductor look like? All right, well, if I look at a phasor for the inductor, it would look like what? Well, it'd be a cosine function. Doesn't a cosine function already start at its maximum and then start spinning? So in this diagram, if this is the current, then wouldn't I have the voltage from the inductor before I get the current? And so your author is trying to say here is what a phasor diagram would look like for an inductor. you would have a spinning stick. But the voltage on the inductor would be 90 degrees ahead of the current. So I already put in the trig function for a resistor. Now I'm putting in the trig function for the inductor. And so I have just added them together. And if that's all I was doing, and I'm not because I'm going to put the capacitor in there, but if that's all I was doing, I would just have to add these two sticks together. And it's a lot easier to add two sticks at 90 degrees than it is two trig identities, isn't it? That's the advantage I want you to see. That's what your author is trying to say. Let's add these together with phasors. They're a little hard to understand at first, but when you nail them, you will be so glad you did. They make your math so much easier. And they're very visual. And that's, I think, why they're hard to learn here at the beginning here. Okay, so I'll say it again. What am I trying to represent by this picture? A spinning stick here. This one for the resistor spins around. It represents this trig function. This one here, this is the voltage on the inductor. It too is a trig function, but it's a trig function that is a cosine instead of a sine function. So it is 90 degrees in front of the voltage from the resistor. And so by adding these two sticks together, I would get the sum of those two trig functions. And it's a lot nicer to add two sticks at 90 degrees than it is to do trig identities. Watch, let's go back to that picture that we had for our phasors a second ago. If we go next, here's two trig functions. Now, unfortunately, these two trig functions are not at 90 degrees because they're a lot easier when they're at 90 degrees. So our job is going to be easier than this picture showed. But this animation shows a blue trig function and a green trig function. They're two sticks spinning around. What is the sum of those two trig functions? They are not in phase. And most of you, before you came here today, probably would have tried this with trig identities. And that's not bad. It's a good first step, but it's a lot of work. It's a lot easier to think of them as spinning stick phasors. And so this green and this blue one, what do you get when you add that trig function with that trig function? And so the red one is the sum of the two. And so all you need to do is add up the green stick and the blue stick and give you the red stick. And so this is just adding up legs of a triangle. This is vector addition. I think that's a lot easier than taking the blue and the green one, write them with some trig identities, and then figuring out what the red one is from that. And ours is even easier because we are at 90 degrees. And adding two sticks at 90 degrees is great compared to the one that's shown here. All right. Well, of course, we're not done. This little animation only shows two sticks. We actually have to, in ours, add three. So what would the phasor look like for the capacitor? So let's add to this our third trig function. Our third trig function is a negative cosine. What would that look like in my phasor diagram? Yeah, it would be down x c, right?
Shouldn't be at the same magnitude of itself.
Now, if they were at the magical frequency, what we'll call the resonant frequency, then they'd be the same length. But in general, they could be different. So, good point. The way I have drawn it, the voltage on the inductor looks like it's a little bigger than the capacitor, so I would be at a higher frequency than this resonant frequency. If I was at a lower one, then this stick would be bigger than that one. Okay? But here's the final step, and here's the beauty of working with phasors, is how do I add these three together? Yep. Wouldn't I combine those two first and say those two come out to be something that is equal to XL minus XC, right? And then the resistor goes over to here, and so there's the result. So I claim that adding these three together would give me something. Let's talk about the something. And then sine omega t, and then some angle phi, right? And this amplitude is really the big piece. It would be this hypotenuse, so it would be an r squared plus an xl minus an xc squared square root. And, oh, and let me not forget my I maximum that I had already factored out at the beginning, and your author did the vectors first and then added them up, or the phasors first. Yeah. Well, I haven't given them any axes. We could now start using real and imaginary numbers and complex numbers, and I think you guys in circuits kind of go that far, but we don't go that far. So I'm just going to say it's a spinning stick, and the only axis that's relevant really is kind of this vertical axis, because this is the voltage. Because the real voltage is the projection of the spinning stick. And the voltage does change. And so in mine I would say this is the real voltage is actually the projection onto the vertical axis. That's why I needed to get this magnitude. Here's the lesson though. The lesson hopefully is a little bit about phasors, or the truth is you're going to do a lot more phasors later on in your education, and the point here is to kind of introduce you to them. So I don't expect you to be real proficient at phasors yet. I know that when you transfer and go to the upper division, they kind of expect you to be able to pick it up kind of quickly. So your author gives you two exposures to phasors, this one here and another one when we do optics in Physics 123. But this is our phasors, and if I then take three trig functions and add them together, I get my answer. And here's what I have. I have then V maximum is equal to I maximum times this R squared plus XL minus XC squared. Or written like Ohm's law, this is now saying the maximum current you get is the maximum voltage divided by this mess of all three pieces. Part of it, the current is being opposed by the resistor. Part of it, the current is being opposed by the inductor. And part of it, the current is being opposed by the capacitor. You need to put all of them together. Of course, the hard part here is they were not in, well, I was going to say they weren't in series, but I don't mean to say that, because they are in series, but they're not in phase when you add them in series. And so when you do the math, you do not get just as simple as what you might have guessed. You might have guessed that, and notice it does not equal R plus XL plus XC, does it? It's not just the resistance of the resistor plus the reactance of the inductor plus the reactance of the capacitor. All three of them are opposing the current, but they are doing it in a complex way that they are out of phase. And so we have to add their opposition and take into account them being out of phase. Some of you have already been exposed to the totality of all of these. I'll say it again, the current is being opposed for three reasons. 1, the resistance of the resistor. 2, the reactance of the inductor. 3, the reactance of the capacitor. All of them together is called the impedance. And so what we say is we have an impedance of this circuit. We have the total opposing amount from these three elements. One can be more dominant than the other. And I think the more interesting occurs when what? Right there. When those two are equal, when XL equals XC, what number do you get there? 0. And so then you just have the square root of R squared, which is just R. And so at that point, you get just a V over an R. That's the magical point I was talking about. If I were to make a plot then of the amount of current for different frequencies, what I would see is at low frequencies, this number is big. But at high frequencies, that number is big. And at mid-range frequencies, they cancel. And so I get a Lorenz shape pattern. And I get a place where I will get a lot of current. I will get a lot of current when the reactance of the inductor and the reactance of the capacitor are equal in magnitude. They're already opposite in direction. And then I get my current. And that's what I was trying to show you. Yeah, a bunch of questions.
Sometimes the inductor and the capacitor are in parallel. So how do you solve for that?
Oh, now if they're in parallel, we won't touch that this semester. Yeah. So, but yeah, you can see then this is the next step. We've only done series. But now that you know all this, it actually wouldn't be too hard to do them in series. I mean in parallel. But I will emphasize that, especially for those of you who aren't in the circuits class, don't expect anything on the test that is not series. Don't start asking yourself, hey, he's going to give me one in parallel. I am not. We'll say that for the circuits class. That's what you guys in circuits will do. You will do in parallel and combinations thereof.
Is this similar to the RMS or?
Oh, and now I want to get the RMS too. I haven't even mentioned the RMS yet, but I got to get to the RMS. Yeah.
What happens to the sine of omega t plus p?
Now, okay, so maybe I'll clear the board here a little bit so you can kind of see this. I haven't forgotten it, don't get me wrong. What I've done is just left it off because this is the maximum. So what I'm really saying here is the current as a function of time is the maximum voltage divided by the impedance multiplied by the sine of omega t plus phi. Okay? And so this discussion here was just equating the coefficients in front of the trig function. And so what I will get is a current that does change with time, and its maximum current is right here, and that depends on impedance, and impedance depends on what frequency you're at. So how much current I get depends on what frequency I'm at, but whatever frequency I'm at, it will oscillate with time, definitely. And let me not forget the phi. How do I get the phi here? This is the other nice thing about not having to do those trig identities. If you'll notice, I got the magnitude of this stick pretty easily. I just had to do Pythagorean's theorem to get the magnitude of the stick. That was the beauty of the phasor. I can also get the phase real easy by using a little trigonometry. Wouldn't the tangent of the phase be what? This height, right? So XL minus XC over R, right? And so again, hopefully you're beginning to see, and maybe not completely understand, that's really not where we're going, complete understand of phasors, but beginning to see how the phasors can be a very powerful mathematical tool, how we can take trig functions, and in this case, 3 trig functions, a sine, a cosine, and a negative cosine, and really add them together fairly easy by using just Pythagorean's theorem. That's the beauty here, yeah.
Is it possible to shorten the range where the frequency? Like you have different specific range, like if it's not just like.
Oh, yeah, so if we study this a little bit carefully, we can see that R can make this thing fatter or wider. Yeah, yeah, yeah. And make it shorter, yeah. Well, I'm treating XC as a positive number because it is 1 over omega C. So it's pointing down. So when I wanted to get the total result of these two sticks, I got to subtract. Well, all right, now bringing up somebody else's question. Somebody else said, well, okay, what that really means is that the current changes with time. So let's say we hook this up, and we hooked it up to one of these meters here. Oh, bummer, I'm gonna run out of good time. And I set the dial here to an ammeter. What does it give me? Does it give me the average current? Because it changes with time? Does it give me the maximum current? I mean, let's start with that phrase, average current. Let's take a close look at this. If I were to plot this current now, and so here's the current. Now remember, it's out of phase a little bit, okay, which in this case, it's a positive phase angle. If I was at a different frequency, it could have been a negative phase angle. But the way I have drawn it in the picture, I have drawn it at a frequency higher than resonance, which means that the XL is a little bit greater than the XC. And so if it's a positive phase, I guess it looks something maybe a little bit like this on my graph. Okay, and so that would be a way of plotting it, what I'll call the old way, not a phasor, but a graph. And so the new way is right here. I got a stick that's spinning. I'm trying to say it's the same as this. And so if I were to plot current as a function of time, it would look something like that. Now, I'm hoping it goes without saying, what's the average current? 0. And what if I turn up or turn down the voltage, or turn up or turn down the frequency? What's the average current? Yeah, so getting a machine to measure average currents is pointless. It goes one way, then the other, one way, then the other. And so we never want to specify what's the average current. That doesn't do us any good. But we could do this. What's the average power? Let me simplify this circuit just a little bit here, and we'll jump back if we have time, but let's just do this. What if I had, as we got started here 2 hours ago, and we had an AC source with just a resistor? What we said then is the current as a function of time would be some maximum value divided by R sine omega t, right? That would be the current. And it keeps changing. And as I'm trying to point out now, it would make no sense to say, well, what is the current? Changes with time. Doesn't make sense. You don't say the current. Bummer. Oh, since it changes with time, I'll say, what's the average current? Well, again, what is the average current? 0. Boom. Bummer. That doesn't do any good. But what does do a lot of good is you can say if current goes one way and then current goes the other way, there would be power consumed either direction, right? And so you could say, what's the average power? And so if I say, what's the average power, which if you're not familiar with the symbol from math, we like to put a bar over it for average. How would we calculate power? Isn't it I squared? And so we could talk about not the average current, but the average power. And the average power is related to the average of the square of the current. Now what's nice about that is the average of the square is a number, right? When you square it, all the negatives go away. And you can add a bunch of squares here. And so what we are going to do is say this can be thought of as the square of what?
Of the maximum.
Okay, the average of the squares. And so we are going to call this the RMS. The RMS standing for the S for square. Take your current and first square it. Then average that, or take the mean of it. And then take the root of it. And this will be very useful. So when I hold up this meter, and what you guys have been using in class is when you get this meter and it says the reading, when it says the current, it's not saying the current is, because it changes with time. It's not saying it's the average current, it's saying it's the RMS. And what's very useful about the RMS is it is the average of the squares. So if you take the RMS and you square it, and then you multiply by the resistance, you're going to get the average power. That can be useful. And so RMS current and RMS voltages are very useful. Watch this then. I'll keep going. How is the RMS related to the maximum? Oh, looks like we're out of time too. Bummer. But if you said the current as a function of time is some maximum times sine omega t, if you take that current and square it, you add it up for one cycle, you then divide by the time of one cycle, you then take its square root. What have I just done? There's the S, square it. There's the average, and then take the root. That's how you get the RMS, as the name implies. The RMS is not the average, but the RMS is useful because when you square it, you will get the average power. And so in this case, if I do this little arithmetic, I will have 1 over the period. I will have an integral from 0 to t. I will have I maximum squared sine omega t dt. That would then be I maximum over 1 period. So then I have the integral of sine squared. And since we're short on time, I'll just do a quick visual picture. But what is the integral of sine squared? Well, it's half of however long you go over. So it's half of t. Oops, I forgot to square that. The t's cancel off, great. And you end up with the maximum divided by the square root of 2. And so that little machine gives us the RMS. And it's not a surprise that the RMS would be related to the maximum. How is it related to the maximum? That's what the math just showed, right? It would be the square root of 2. I didn't do it for voltage, but let me have you do a quick calculation. What was the maximum voltage of that wall when I plugged it in? 170. Take 170 and divide it by the square root of 2. What do you get? 120. And that's why for the longest time we've been saying, what's the voltage of that wall? 120. Now, we didn't mean it was always 120 because it changed with time. We didn't mean it was average, no, because the average is 0. We meant it was the RMS because when we square that, we get average power. Not average voltage, average power. We take the RMS to square it to get average power.
So can we calculate power with just VI, by the way?
All right. All right. Well, good luck. Have a good Thanksgiving. Lots of homework.